We are now recording. Okay, so in Code Composer Studio, let's actually create a new Code Composer Studio project. Okay, and then we're going to use, there's actually two sets of compilers. We're going to use the TI compiler throughout this course. There's a GCC compiler for the ARM, but the GCC assembly is a little different than the TI assembly, which he uses, Kyle assembler actually in the textbook. And then, so create this project called first assembly. And then we want to create an empty project without a main.c. If you've already clicked on create one with a main.c, then just delete main.c. Okay, because we're going to write a main program in assembly. Okay. So first assembly, empty project, and then finish. Okay, so we've got our project with the startup files, but no main program yet. So in Chrome, go to the course website, so csserver/Richardson, and then EE354, and then lectures, and then right click on main.s, and then say save as. And then browse to where your workspace is. So I think by default, it's like under, there's no shortcut to that. So like on this machine for me, it's C, users, and then my username, AR63, and the workspace version 10. Then you should find a folder there that's the same name of this project you just created, first assembly. So save your .s file there. Now what we're going to do with these other three files, we're going to be using them throughout at least the rest of the course with this microcontroller. So what we're going to do with them is actually create a separate folder, and then we'll link to the same source files every time. The reason I want to do it this way is I may provide updates to sio.c and uart.c. And if we put them in one folder, we can just put new versions in there, and then by linking to them from our projects, we can update them without having to update all of our projects, if that makes sense. So right click on SIO, that stands for Simple IO, and I'll talk a little bit more about that. And then in your workspace directory, what I recommend you do is create a new folder, call it EE354 SRC for source. 354 SRC, or whatever you want to call it. And drop this file there, and then save the two UART files to the same location. Now, back in Code Composer Studio, you should see it's found main.s. You might have to right-click on the project and say refresh, or I don't see refresh. Yeah, F5, refresh. But we need to add these other three files to our project. And we're going to link to them, but so you do that by right-clicking on the project, and then under Add Files, go into the workspace, the EE354 source, and then Control A will select all three of those. And then or highlight all three of them and say open. Then now here, by default, mine says copy. We're going to actually link to the file. So it won't copy them into this project directory. So it will actually use the source in the EE354 source directory. So again, if I provide updates, you can just dump them in that folder, recompile your projects. You won't have to add them again or anything like that. If we copy them and we updated the stuff in the source, then the copies wouldn't be updated. Okay, so this is a convenient way to, allow me to update the software. Okay, so the UART-C we've already used, right? It actually provides for serial output. And then Mark found actually that there was a terminal built into Code Composer Studio. I wasn't even aware of that, but if you go into View and Terminal, and I still prefer to actually use PuTTY instead of the built-in one because the PuTTY one's open in a second window. But with the simple IO.C, these are one-line functions that make it really easy to do IO from assembly. Okay. So part of the problem with doing function calls with multiple arguments is that you have to use the stack. And we're going to talk about how to pass arguments on the stack, but it's a little advanced. That's later this week. Okay. So at least initially, it's much simpler to, if we want to print out a value, put the value in register R0 and call print int, which in turn calls printf with the right format specification, because we don't really know how to handle strings yet in assembly to get the format specifier and put them both on the stack. So that's all this does. It provides very simplified versions of printf primarily for printing integers, unsigned integers, printing an integer in hexadecimal if you want to see the hexadecimal, printing a new line, or printing a space. At this point, I've got one routine to actually just read an integer. It returns the integer in R0. And we'll learn how to interface between C and assembly. It's not hard. I mean, these are all C programs, actually, that we're going to call from assembly. And so it's really easy to do, but we do have to cover that calling syntax. And then you can see, I'm going to add some additional stuff here, but I didn't have time to do that over the weekend. But this is kind of provided now for you. But if you look at main.s, and here's where things are, you get a little, let's see if I can, I guess I'm going to change the font size here somewhere. Hopefully that's readable. Well, you've got it in front of you. There's some stuff here at the beginning that we'll talk about. Okay. There are a couple of strings here. This is how you define a string in assembly. And again, I don't really want to get into that today. We don't need to print out. This prints out strings, but in the next assignment, you're just going to print out integers. But this essentially sets aside space and memory, puts this string in memory. All 10 is a new line character, and 0 does the null termination of the string. So what you'd find in memory are these. This is a convenient way that prevents me from having to type these in hexadecimal. Okay, each individual letter. I can just say, put it in double quotes, and the assembler automatically converts each character to ASCII and stores it in memory, and then puts in the new line character. You can't put \n inside the double quotes in assembly. It actually would store the / as an ASCII character, and then the letter N as an ASCII character. And then you can't put /0 either, like you can in C. This is assembly language, it's not C. Some assemblers allow you to do that. And then this defines puts a name to the address where that string is stored. So I just call them string 0, string 1, string 2. Okay. And that's not really important at this point. I mean, we're going to keep this basic syntax. What we're going to be mainly messing around with in our assembly language programming is, you know, here's my main routine. And we put a label there when we compile our program and run it. You know, the startup code calls our main routine. There's some couple lines here that stop the watchdog timer, just like we have in the past. But then here is where we put our code. So anything that needs to be run once before we go into a while loop should go here. Remember, we have to do the output initialization for our UART. So this is a branch. This is a function call in assembly. Branch to call that output init, and then it returns to the next location. And then the rest of this is just kind of some examples, and we'll talk a little bit about this today. What I found interesting about the ARM, and I haven't programmed the ARM in assembly before, so I'm kind of learning this along with you guys. There is no way to move a 32-bit constant into a register that I've found. Okay, you have to, the move actually will just take a 16-bit value. So this actually, but what you have to do is, here are two 16-bit values, and then this will shift a value left by 16 bits, and then add it into a register. So it's a way to learn, this is FFFF, FFFE, which is actually a -2 in 2's comp, 32-bit 2's comp. If you actually, this move would just move zeros into the upper half word of register 1 into the upper 16 bits, and then all ones in the lower 16 bits. But it doesn't look like the ARM has a way in a single instruction to move a 32-bit constant into a register. You can do it from memory. You can move a 32-bit value from memory into a register, but there's no way to move a constant value. You'll see that another way to do this is actually put the constant in memory and then load it from there. So this is actually just setting up to put -2 into register 0. We can then just print that out, print int. Okay. Function call, okay, and that's all you have to do here with these simplified I/O routines. Put the thing you want to print in register 0. If you want to print it in hexadecimal, call print hex instead of print int. We'll change that in just a second. This prints a new line. Okay, we got low-level terminal I/O here. Sometimes your terminal may look a little screwy. Actually, in our UART routines, I think it's set up so that every time it sees a new line character, it automatically does a carriage return. Okay. That's kind of keeping with C-style program, where we normally just do \n. But that typically translates on most serial terminals into a new line. A new line would actually just take you down a line. We typically want to do a carriage return. If your terminal's not doing that, don't worry about it. It's not that big a deal. This is loading an address into a register R0 and then printing it. Okay, so again, to print a string, remember this is printing string 0, which I think is just, it was just a first assembly, something like that. This is printing a prompt, okay, and then this is going to read an integer. It returns the value in R0. Now, after that read, I actually want to do a print line, because when you enter something in and see it actually, and then press carriage return, it would actually return, on my terminal, it was returning to the same line, and then printing anything out would overwrite whatever I typed. So I printed out a new line there. But one of the things, every function call, and we'll get into this, but functions don't have to save the values in R0, R1, R2, and R3. So you have to be aware of that if you've got something stored in R0, you make a function call, when that function returns, whatever you had there may be wiped out. Okay. Functions are required to save the other registers, but not the scratched registers, R0 through R3. So to save that, I move R0 value into R5, make the function call, print the next string, move that into R0, and then actually now I move the number 2 into R0, multiply the value that I entered in, which is an R5, times 2, and then that gets stored in R0. and then print in. And then this goes, there's a bunch of stuff. We'll greatly simplify this, and then branches back to the while one. So that's our infinite loop, kind of like what we've been doing in C. Some instructions and an infinite loop. Okay, so at this point, this is where we cross our fingers, and then actually you can do the release version so it doesn't start the debugger. I need to plug in my board. Okay, so mine's actually finally is building. And then download it with this, where it says flash, this little icon should transfer the program to our board. And then if you open up view and then go down to terminal, building terminal, you have to click on this little icon to say you want a serial terminal. Okay. And it pops this up, COM4, the right baud rate, and then click. And then you'll see the, when it finally loads, you should see the output here is COM4. Let me reset, no, there it is. So if you remember that what this did, got rid of my terminal, it's still there, okay. What our program does at this point, let me reset it because it looks like it, no. It prints that string and then prints this prompt, enter an integer, and then it should display, oh, we have a bug. There's a, this is gonna mess it up. If I enter in like 45, remember the bug in the scanf implementation eats the first character. So 45 it interprets as 5. So the way to work around that is 045. It's unfortunate, but that happens every time we use the scanf and this for this TI compiler. And then it's just doing this in an infinite loop. Okay, is this working for everybody? What's it doing? It won't compile. It won't allow you to type into the terminal. Make sure you click in the terminal so it redirects to that. Anyone else get the work? So working for. Okay, so what we'll do for assembly language programming, again, there's a lot of stuff in here. Let's strip this down to, so, right click on this and then just say copy, and then right click and say paste, and I don't know, whatever you want to call it, simple assembly. And let's open up the main program for that. Okay. So you've always got the first assembly to go back to, but we can get rid of these string definitions here. Okay. We're going to go to kind of a bare minimum program. So let's actually just move the number 100 into R0 and then print it out. And we'll get rid of everything else. So call print underscore int. Don't get rid of the branch back to while one at the end. Now, we may also want to well, let's do this. We'll run this, and we'll see what happens, and then we'll see why we probably want to add a new line. So at this point, build it. Not remade because of errors. Oh, why did I say call? It's BL, isn't it? Is the no one said anything. BL is our in assembly. I don't know where call came from. I said call the print end and then just type in call. Okay, so but the way you call a function is we branch to that function and then we return back from it. So hopefully this will build. And then now we flash our board. I don't think it matters whether you say yes or no there. That's because we copied over an existing. Now, what I'm expecting to see in our terminal window is just 100, 100, 100, 100, 100. So bring back up my terminal. And that's all it's doing. It's printing 100, 100, right after no line feeds or anything like that. So, and this is why you typically want to, let's actually have it multiply by 2 every time through the loop. Okay, so that should be fairly simple. So it prints it out. We'll add a new line here. So we'll get separation between the lines. And then now I'm going to multiply. So I actually want to move my move instruction outside my while loop, right? Because I want to initialize it to 100. At the beginning of my while loop, it's not going to do me any good to multiply it by 2 at the end of the while loop because it's just going to set it back to 100 at the beginning. So I'm going to cut this line, move it outside my while loop. Going to print it, multiply R0 by 2, and then go back and print it again. Now, there is a bug here. You see what the bug is? Get rid of this comment. Well, let's run it and see if we can figure out what it's going to do. Okay, so I've got the syntax for multiply wrong, but so it won't take just a register. Oh, I guess it has to be register, like that. So I was hoping it would multiply register R0 by 2, and that's still not right. So let me look it up. So these are all in the back of your book.
You just make another register, put R2 and all over, and then multiply R0.
Yeah, it looks like I'm going to it won't multiply won't take a constant. So I'm going to have to actually move the 2 into a register. So move 2 into register 1, and then multiply. I think this will multiply the 2 registers together and store the result in R0. Okay, so that appeared to compile. Let's see if we can rewrite this. And view terminal. Okay, and I'm just seeing 20 repeatedly. Okay. The bug is that I'm relying on having something in R0 and these function calls actually preserving R0, right? I moved 100 in there, but then I call a function. And anytime you have a function call, you can't rely on it preserving R0. So we could actually push it onto the stack and pop it back. That would be one technique. Or we could move it into another register. That's probably the easiest thing to do at this point. Okay, so R4 through R12 are all preserved. But print new line, they could overwrite R0. That's actually what is going on here. So you got to be careful of that. That anytime you make a function call, use the BL instruction. That the contents of R0 through R3 are not preserved. So let's actually just move it into R4. R4 times 100. Here I'm reinitializing R1. That's okay. Now, and then this is going to take the value in R4, multiply it by 2, and move that. Actually, I want us to keep it in R4. But my print int, it will only print the value that's in R0. So I've got to move what's in R4 back to R0. Okay. So, I don't know, you have to think about what's going on here at every step. Right? So anytime I want to print something, I need to put it in R0. So now if let's see if this will compile. Now this is gonna, I hope, double the number and print them out so quickly. You're probably not going to see the first 100. Okay. And copy it. This is one of the reasons I actually like to have PuTTY just open in another window. I can see the initial output all the time. This Code Composer Studio keeps changing, or they call it the view or aspect. Oh, that didn't appear to be working. So I'm getting nothing but zeros. So I multiply R1 by R4. Is R4 preserved, or maybe R?
If you hit reset, you can briefly see some numbers stuff. And then it says zero.
Say again?
If you hit the reset, you can briefly see some increase in numbers here. And then
Oh, it wraps around.
Isn't there nothing?
Oh, that's what it actually gets. It gets to a 32-bit 0 and then stays at 0. That's what's going on. Yeah. Because so it is working, but it wraps around. So reset the processor. Let's see. I guess we could prevent that by just adding one. Add. I'm just trying to get some basic output here. Because your project, I'm going to have you redo that random number generator, but in assembly. And he provides the code for that in the book, actually. So. And it looks like it got into some, my fix wasn't quite enough. But need to come up with a let's just add one and forget the multiply. So I get rid of this, add one to R4. Did I actually hit debug? This thing never came back. Download the must have hit debug last time. And I think I'm going to have to reset my Code Composer Studio, but did it work for anyone else? Just adding one?
Yeah.
Okay. Looks like my thing is kind of locked up. Okay, so I'm going to talk a little bit more about, we have a few minutes here to talk about some more assembly language programming, and in particular, if you have your book with you, if you turn to the back, got this assembly language reference, and you look on page 433. So last time we were talking about addressing modes, or addressing modes. And there's a bunch of different ways. You can move a value from register to register. You can move an immediate value into a register. Again, there are restrictions on immediate value. It has to be only a 16-bit value. It clears out the upper half of the 32-bit register, but that's because the value is actually hard-coded into the instruction, into the 32-bit instruction. There's only room for a 16-bit value here, so you have to play a trick to actually load the full 32 bits. One of the operands or addressing modes is what they call this flexible second operand, or op2. And an example is with the add instruction. Remember, this means an optional destination register. If you leave that out, the destination register is actually the second register. And then I think in the add instruction, it's written like that. So what you can do here are things like add R0, R1, and 100. So this would be R0 is R1 plus 100. That makes sense. We did something like that in this little example. But you can also this stands for logic shift left, and then followed by the number of bits. So this is going to do R0 is equal to R0 plus R1 shifted left by 16 bits. So this would be, I'll show you in just a few minutes how to actually move a 32-bit word into a 32-bit constant and into a register. So until you get a lot more familiar with programming the ARM and assembly, you're going to be always looking at these references in the back of the book. And there are a number of variations on each of these different instructions. The addressing modes, there are different suffixes you can add to each of the instructions. You can do logic shift left, arithmetic shift. I'll talk about those in just a minute. Different operations here, okay, for this flexible second operand that they allow. Okay, so I think that finally gets us through all the different addressing modes, and we'll come back to these. I know it's a lot to absorb. Memory access. Use move to move values from one register to another, okay, full 32-bit moves. Use LDR and STR to load and store from memory. From to memory. So LDR, R0. So that's going to treat whatever's in R1 as an address, go to that address, get the 32-bit value that's at that address, the next 4 bytes, and load that value into R0. Now, we've got yet to talk about how do you load an address into R1. Well, that assembly first program actually showed you how to load a label, str0 into a register. That's how you do it essentially. But so the C syntax here would be R0 is dereferencing that address. There are variants on this. We'll talk about using the stack pointer. But this is going to add 4 to the stack pointer. It won't actually increment the stack pointer value, but it'll form a new address, which is 4 above whatever's in the stack pointer. Go to that memory location, go onto the stack, essentially, move a value on the stack into R0. So R0 is stack pointer plus 4. Now, these are going to be 32-bit or 4-byte memory loads. Sometimes you just want to get a byte or 2 bytes. So there are corresponding variants. LDR B will go out and get that byte, and then it loads it into the least significant byte of the 32-bit register, and zeroes out the upper 3 bytes. Now there's another one on this that's another variant that's LDR SB. So this loads a byte, or the SB variant loads a signed byte. And if you do the LDRB, it will zero pad, fill the other 3 bytes with zeros, or it'll do what's called sign extension. So for example, if you have, and you have to keep track of, you know, whether you're treating a particular byte value as an unsigned value, in which case its range can go from 0 to 255, or a signed value, in which case it can go from -128 to +127, right? So when you load that in, you want to set that 32-bit value, if you're going to do arithmetic with it. You want to set that 32-bit value appropriately. You know, if it's unsigned, the upper 3 bytes should all be zeros, right? So if so for example, I'm gonna use FF, which that's 255 unsigned, right? But it's -1 signed. If you load it in using the LDRB, the result would be 0000000 FF, which that's 255 unsigned. If you load it in using LDRSB, it takes whatever the most significant bit here is, you know, now it's a 1, because this is a negative value, and fills the rest of this with that bit. So this would be the LDRS, and so this is still a -1, right? Now, in signed, if it were actually 100, in that case, the signed bit is 0, and if you loaded 100, you get the same result in both cases. So it would be a positive 100. I mean, it's a little strange, but again, you have to ask yourself, do I want to load this thing? Am I treating this byte as a signed byte? Am I doing signed arithmetic with it? Or unsigned byte? You don't have the C compiler helping you out where you'd say, this is a char or an unsigned char, right? And then the C compiler makes sure to do the right arithmetic depending on the data type. You don't have data types. As the programmer, you have to keep track of the type of each piece of data that you're working with, whether it's signed or unsigned, whether it's a byte or 2 bytes, what he calls a half word, or 4 bytes, a full 32 bits or a full word. So there are also variants for LDR-H and LDR-SH for word or 16 bits. And you have similar options for the store routine. Okay. You can, if you store a byte, it just pushes the least significant byte to that memory location and only changes that byte in memory. Or if you use STRH, it's going to push out the lowest 2 bytes into that memory location. Just using LDR or STR, those are full 4-byte instructions. It's going to retrieve 4 bytes from memory, or with STR, it's going to store 4 bytes in memory. There aren't signed and unsigned versions of the 32 bits because that's our maximum size, right? You've got it stored in as 32 bits in memory. You're just going to copy those 32 bits. It would be the same whether it's signed or unsigned. So, and move and only move 16-bit immediate values to move 32-bit value. Here is one method. It is certainly not the only one, but I'm going to move one 16-bit value into R1. This is actually going to clear out, zero out the upper half word, the upper 16 bits. And then I'm going to move into R0, another value. And then I'm going to just add these two, while shifting left by 16 bits. So this is a logical shift left of 16 bits of R1. So it'll take the lower 2 bytes, shift them 16 bits to the left, so that'll move them into the upper 2 bytes, and then add the 2 results. And so this will give me R0 is equal to OA, OA, OB, OB. There are logical operations, and I'm not going to go into details on these, but there's and or, and we'll be using these a lot once we start accessing the control registers. And I've talked about you have to mask off bits, or if you want to set certain bits or clear certain bits, you use and oring operations. There is also exclusive OR. There is, what is it called? It calls it BIC. It's binary. It ends with the negative of the second operand. Okay. So here's some example code. Load R1. So you'll see that we can label an area of memory in our assembler and assign a name to it, like I did with str0. But there I use like the ASCII thing, but we can also just store a number at a particular location. So I can load that number. So this is essentially R1 is equal to the address of N. And then so the first one actually doesn't load N, it loads the address of N. Then I can get the value. So memory accesses are typically 2 instructions like that. One to get the address of the location, the other then to actually get the value. And then I can OR R0 with R0 and 1. So this is going to take the current value of R0, which contains N, or that with 1. This is a binary OR. So it's just going to set the least significant bit. It's going to read the value of N, set the least significant. And you can write that as, I would typically write that as, 0x01 or something to indicate I'm just setting that 1 bit. Since I'm ORing all the other, and this is a 32-bit operation, but ORing with 0 doesn't change the value, right? So it's only when to set that least significant bit. And then write it back into memory. All right, any questions? I'll stick around here for a few minutes if anyone has questions about the 310 exam. I hear there's an exam today, so got a lot of you in here. So just going to be coming up to my office. I'll just stay around here for a few minutes.
Oh. Yeah, I know. Well, that would be weird here. And you were confused with all I could see is every so L and I kind of thought there was an E after it. What? Yeah, probably. I've been there before. I go over like 1 year. I still look over 1 year. It's just good tests. You know, Delta and CD. I just don't remember which one for which. You know, Delta. That makes sense. I don't remember where you talked about it. I need to just look over the level page and whatever results. I need to do that again probably. Yeah, I can't imagine.
It's an ampersand. It's supposed to be the address of a variable, but I can't draw an ampersand.
See, I thought it was an L at first. Like, I'm so. And it really is bad because I'm right in cursive, so that really wasn't L.
Yeah. And yeah, it can never draw that ampersand there.
I don't know.